All right, this video is for the Unit 2 Lesson 7 Ready, Set, Go problem set. And in the first section, we're asked to fill in the table of values for each function. And so in question 1, I'm given the function f of x equals 3x plus 5. And a couple ways I could do this. I could recognize that this is in slope-intercept form, or I could input some values to the function and fill out the table that way. So for example, I like to start with 0. You could start with where x is -1, but I could substitute 0 for x, and I would get 3 times 0 plus 5, which is just 5. And that makes sense because in y equals mx plus b form, 5 is my b value, which is my y-intercept, so the ordered pair 0, 5. I could then find f of 1, again by substituting 1 for x, so this becomes 3 plus 5, which is 8. Or I could find f of 2 by substituting 2 for x, so this becomes what, 6 plus 5, which is 11. Or, again, I could recognize that this 3 is my slope, which is my constant rate of change, which tells me what I need to add by to fill out the table. So since 11 plus 3 is 14, and since 2 plus 3 is 5, I could also find missing values that way. Now, number 2 is really similar, but it is a little bit harder because the only thing that is different here is that I have x minus 1 instead of just x. So let's fill this out first by evaluating g of x. So what I mean by evaluating g of x is plugging in values or substituting values of x into the function g of x and getting a value for g of that number. So just like we did, I guess I'll just start with -1. My brain just really likes to start with 0. If I substitute -1, I get 3 times -1 minus 1 plus 5. So that is 3 times -2 plus 5, which is -6 plus 5, which yields a -1. When I substitute 0 to evaluate g of 0, I get 3 times 0 minus 1 plus 5, which is -3 plus 5, which is 2. When I substitute the 1, I get 3 times 1 minus 1 plus 5, which is 3 times 0 plus 5, which is 5. And you might be noticing that the values in my table are starting to become the same as the table for number 1. And it is true that this pattern will continue, so I'll get 8 and 11, and we could prove that by continuing to evaluate g. But here's what I want to point out. This is also in y, well, it's not exactly in slope-intercept form, so let me take that back. But this is in a form where I have my slope, I have an expression for x, but this time it's x minus something, and then I have my plus 5. So because this is x minus 1, 5 is not my y-intercept, but what this actually tells me is that when x is equal to 1, right here, that 5 is my output. So I could think about this like when we did arithmetic sequences in our first unit, that sometimes my sequence started with a number that wasn't 0. So in this case, I'm looking at the 1. And then that constant, if I have x minus 1 in here, is still the output. That 3 is still telling us by how much we are changing. And again, since this is in the form of a linear or arithmetic function, I'm going to see an addition of 3. So let's use that reasoning to fill out the table in number 3 and probably number 4, because what I notice is that each time I still have this 3 being multiplied, that's still going to give me my constant rate of change or my slope. But what is changing is the expression in here is no longer just x, and it's not x minus 1, it's x minus 2. But I still have the same constant 5 plus 5 that I had in the other two equations. So what this tells me is that when x is equal to 2, so right here, that my output is going to be 5. And that this m, my constant rate of change, this tells me that I'm increasing by 3 each time, so by adding 3, or I could work backwards and decrease. So I would get, let's see, a 2, a -1, a -4 if I work backwards and subtract 3's. And again, if you're not sure about this, you could prove it to yourself. Let's just evaluate h of -1. So what I mean is substitute -1 for x. So this becomes 3 times -3 plus 5, which is -9 plus 5, which is -4. So it checks out. I get -4 when I substitute -1 for x in my expression, or rather my equation for h of x. So to really understand this, it really ties back to some stuff we did in Unit 1. All right, number 4 is really similar, but now I have x plus 1. And x plus 1 is the same as x minus a -1. So one way of knowing what to do here is to know that when my x value is -1, that my output should be 5. And again, just like the other 3 tables before this one, I'm increasing constantly by 3. So I've got 5, 8, 11, 14, 17. And again, I could check this. I could evaluate k of -1 by substituting -1 for x. And I would get 3 times 0 plus 5. Remember to follow the order of operations, which yields 5. And it doesn't help or it doesn't hurt to check another point. So if I evaluate k of 3, I'm going to substitute 3 for x. And so when I clean up what's in parentheses, that becomes 3 times 4. 3 times 4 is 12. 12 plus 5 is indeed 17. So we could check our table that way. Oops, that was a check mark because we checked our table. All right, now when I get to the next couple questions, let's see, do these continue on? Oh, they continue on. Similar thing happening here. Oh, I'm noticing a similar thing in these two equations, except now I know this models an exponential function. And I know our text might use some different lettering, but for exponential functions, I could think of them in the form of y equals b times g to the power of x, where g is our growth factor. With sequences, we call that a common ratio, but it's the number by which we are multiplying. That's supposed to be a multiplication symbol, but it looked like the variable x. And b is still our y-intercept. So again, I could find this by evaluating. So I could evaluate p of 0, 3 times 2 to the power of 0. And I know that is the same as 3 times 1, which is the number 3. And then if I evaluate p of 1, so 3 times 2 to the power of 1 is just 3 times 2, which is 6. But what I'll observe is that this gives me my y-intercept. This number with the exponent tells me by how much I'm growing. And so I'll see a multiplication pattern of 2 here. So that means if I continue as x increases by 1, I should get 12 and then 24. And then if I work backwards, 3 divided by 2 is 3/2, or you could put 1.5 there if you prefer decimals. So in number 6, I could use the same reasoning, that when I have x minus 1 here, instead of this number being my y-intercept like it was over here when this was essentially x minus 0, so I started with 0, I could now start with where x is equal to 1, and that is going to be my number 3. This 2, the number that is being raised to a power that has the variable x, or in this case x minus 1 in it, is still our growth factor. So I'm still multiplying by 2. Working backwards, I could divide by 2. We said that's 3/2 or 1.5. And then working backwards again, I could divide by 2 again, and that's 3/4 or 0.75. If this is confusing, you can always evaluate this, but it can get tricky with negative exponents, right? So if I evaluate q of -1, that is 3 times, I don't like where they put the parentheses here, times 2 to the power of -1 minus 1, which is 3 times 2 to the power of -2. And then I would need to remember that that is the same as 3 times 1 over 2 to the power of +2. So that is 3 times 1/4, which is 3/4. So we can evaluate this equation to fill out this table as well. And there's not really a right or a wrong way, but sometimes I like to try one method and check it. So as we continue, these next ones are really similar. In number 7, again, I could see that this is my starting value when x is 2, and this is by how much I'm growing. So when x is 2, my value is 3. Since I'm growing by a growth factor of 2, that means I'm multiplying as x increases, or I could think of dividing as x decreases by 1. So I would have 3/2, 3/4, and 3/8. And feel free to use decimals if you prefer. I love fractions. They are friendly. All right, number 8, similar to one of the ones we did a second ago, I could think of this as instead of x plus 1 as x minus -1. So this tells me my value is 3 when x is -1. So I would have a 3 here, and then I'm continuing to grow by a factor of 2. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48. And it never hurts to just check one of those values. So if you evaluate s of 3, that is 3 times 2 to the power of 3 plus 1, which is 3 times 2 to the 4th power. And let's see, that is 2, 4, 8, 16, and 3 times 16 is in fact 48. Okay, the rest of these are going to be very, very similar to those first several problems. So I would encourage you to maybe fill out one of the tables, either by evaluating the function or recognizing that this is in the form of y equals mx plus b. And again, since this is a plain old x here, I know that 2 is in fact my y-intercept, and that I am decreasing by a constant decrease of 5. So I'm subtracting 5 as x increases by 1. So 2 minus 5 is -3, minus 5 is -8, minus 5 is negative. Man, my brain just like stopped working for a second. Is what, -13? And then if I were to work backwards, this would have to be a 7 here. Okay, so using the same reasoning as before, if I notice that the only thing that's really changing here is that I now have an x minus 1, that means that my value 2 will appear when x is 1, and that the rest of my table will be like the table in number 9 was. So let's see, we would have a 7, and then working backwards, that would have to be a 12. All right, same reasoning in number 11, that when I have x minus 2 here, my constant is not my y-intercept, but it's the value of y when x is 2. So that means this is -3, This is 7, 12, and 17. And then lastly, number 12, kind of similar to what we've seen already. If this says x plus 1, I could think of that as x minus -1. So when x is -1, that's when my y value is going to be this constant 2. So I would have 2, -3, -8, -13, -18 in my table. And again, you can always check that by evaluating. So h of 3 is -5 times 3 plus 1 plus 2. I'm just substituting 3 for x. So that is -5 times 4 plus 2, which is -20 plus +2, which is in fact -18. Okay, the set problems are not going to relate to the lesson we did in class today, but they're going to go back to those properties of powers from before fall break. So you might want to look at that reference sheet, but we do need to internalize and understand those properties. So each of the expressions can be written using either radical notation or rational exponents. So rewrite each of the given expressions in the form that it is missing. So if you just look at, we've talked about this quite a bit in class, but if you look at this form, whatever number is here is going to become the numerator of our rational exponent, and then the index of our radical is the denominator. So in number 13, in radical form, that's like the third root of 5 squared. I just want to note that's the same as saying like the third root or the cube root of 5 in parentheses squared. Those are equivalent. To write that as an expression with a rational exponent, that would become 5 to the 2/3 power. In number 14, we're given an expression in exponential form with a radical exponent. So same idea, my denominator becomes the index of my radical, and my numerator tells me what power to raise that to. So I could either write this as like the 4th root of 16 cubed, and that is the same as the 4th root of 16, all of that in parentheses cubed. I know that in middle school you probably learn PEMDAS, but I tell you in class often GERMDAS, like grouping, exponents and radicals, multiplication, division, addition, subtraction. It's because exponents and radicals kind of fall in the same place that, that these two forms here are equivalent. Okay, oh, this one, number 15, so much fun. So in radical form, I would probably want to take this one step at a time, and I would want to just start with that index of 3, and I would write this as like 5 to the 7th times 3 to the 5th, and then remember that like when I have like the cube root, so my index of 3, I could think of that as to the 1/3 power. But what I do want to remember is that well, first of all, I think the way we wrote this might be an acceptable answer, but remember that you can distribute an exponent over multiplication. So I could also distribute this exponent over the multiplication of 5 to the 7th and 3 to the 5th, and this would be the same as 5 to the 7/3 power times 3 to the 5/3 power. All right, 16, we have this in exponential form. So kind of like we did the last one in 2 steps, it works better for my brain to do this in 2 steps. So I notice that these both have, both of these expressions have a rational exponent that has a denominator of 3. Remember, in math, rational is a fancy word for fraction. So I might first start by changing this to the cube root of 9 squared times 9 to the 4th. And from there, I can combine those, the 9 squared and 9 to the 4th, since they have the same base. Note that I could not do that in number 15 because 5 and 3, the bases of this expression, are not the same. So I could further combine those by using my rules of powers, that when I multiply two powers of the same base, I add their exponents. I could have also done that here first. Like I could have started by adding the exponents. And again, I can do that because both of these have a base of 9. So 2/3 plus 4/3 is 6/3. And then I could get to my radical form that way, whichever one's easiest. All right, in number 17, I'm going to do this one in 2 steps like we did number 15. So again, the index of my radical, that little number, tells me what root I'm taking. So that's my 5th root. And this becomes x to the 13th times y to the 21st power. And then all of that raised to the 1/5 power. Because the 5th root, like taking the 5th root of something, is the same as raising that thing to the 1/5 power. Sorry, I know I'm a little obnoxious using the smiley face, but okay, so from there, I could also further simplify this by using the property of powers that allows me to distribute exponents over multiplication or division. So I get x to the 13/5 times y to the 21/5 power. But since x and y have different bases, they are different bases, I cannot further combine those. Oh, number 18, this one's going to be really fun. So in radical form, I have the cube root of 27a to the 5th b squared. So again, I might start by writing this as 27a to the 5th b squared to the 1/3 power. And again, if I distribute that exponent over multiplication, this becomes 27 to the 1/3 power times a to the 5/3 power times b to the 2/3 power. And 27 to the 1/3 power is the whole number 3, because the cube root of 27 is 3, and that's because 3 times 3 times 3, which is 3 cubed, is 9 times 3, which is 27. So I could also write this as like 3a to the 5/3 times b to the 2/3 power. Oh, these just keep getting so much more fun. All right, number 19. Oh, yuck. Sorry, I'm like really excited about this one. Same thing, I'm going to take my index first. And I'm going to think of this as like 32x to the 13th over 243 y to the 15th, all of that to the 1/5 power. And I could rewrite that as like 32 to the 1/5 power times x to the 13/5 power, using that property of exponents, over 243 to the 1/5 power times y to the 15/5 power. So I could simplify this a little bit further. I'm pretty sure, let's see, 2 times 2 times 2 times 2 times 2. So that's what? 4 times 4 times 2, which is what? 16 times 2? Okay, I was confirming that this is in fact 32. So 32 to the 1/5 power is the whole number 2. Sorry, this equal sign goes with what's above it. Just going to push that over there. I would still have x to the 13/5 power. Now I'm wondering if the 5th root of 243 is 3. I think it might be. Let's see, 3 times 3 is 9. Another 3 times 3 is another 9. So this becomes like 81 times 3. which is 243. So I could write 243 to the 1/5 power as the whole number 3, and I could simplify this since 15/5 is the number 3. So this is a pretty complex problem. All right, this last one, woof. Right now, the way this is written, we could not combine this all as one radical, because what I notice is we have different denominators. So this has the denominator of 3, where the other two rational exponents have the denominators of 2. But what we could do is we could get a common denominator of 6, since 3 times 2 is 6. So I could rewrite 9 to the 3/2 power. If I want that to have a denominator of 6, I would multiply 2 times 3 to get 6 and 3 times 3 to get 9. Then this would be s to the 12/6 power, and this would be t to the 3/6 power. So again, I just rewrote these 3 fractions with the denominator of 6. So now we could say this is the 6th root of 9 to the 9th power times s to the 12th power times t to the 3rd power. I think both problems 19 and 20 are like exceptionally difficult. So I don't know if I would stress over those as much. I think those are great challenge questions. I think the other ones before it are a little more accessible, but I know this is a hard concept for students at first. All right. It tends to be that the set section is the most difficult, so let's take a look at the go. And this should be a throwback to things we've either learned before Algebra 1 or that we've learned this year. So given the function, find the x-intercepts and y-intercepts if they exist, and then use them to graph the function. So remember, the y-intercept occurs when x equals 0. That's what puts us on the y-axis. So similarly, the x-intercept occurs when y equals 0, and the x-intercept is just a point on the graph where the graph of a function crosses the x-axis. So again, that is where y equals 0. So if I want to find the x-intercept, actually let's do the y-intercept first, it's going to be a lot easier. If I want to find the y-intercept, I'm going to substitute 0 for x in this function. So in other words, I'm just going to find f of 0. And I get 5 times 0 minus 4, all of that minus 10. So that is 5 times negative 4 minus 10, which is negative 20 minus 10, which is negative 30. So my y-intercept is the ordered pair 0, negative 30. The next part is harder though, and we haven't done a lot with solving equations this year. I suppose there might be other ways to do this, but if I want to find the x-intercept, I need to set y, which is the same as f of x, equal to 0. So if I take my equation, if I set that equal to 0, what makes this harder is now we're going to have to both evaluate in the right-hand side and use the steps of solving an equation to work backwards and find x. So what you could do first is you could either distribute that 5 or you could add 10 to both sides. It doesn't really matter which you do first, but my guess is that in middle school, you would have learned to distribute first. So 5x minus 20 minus 10. I could combine these like constant terms to be minus 30 or negative 30. Then I could add 30 to both sides to get 30 equals 5x. And then when I divide both sides by 5, I get that 6 is equal to x. So our x-intercept should be the ordered pair 6, 0. All right, so I am just going to sketch a graph. We should probably really graph this, but I am making this video at like 12:30 in the morning, so I'm going to just sketch a quick graph. We know this is a linear equation because it's in the form of y equals m some x stuff plus or minus a constant. And I didn't use b there because -10 is not our y-intercept. That's what we should get when x is 4. But I am just going to sketch a quick graph. So let's just say that these are my x and y axes, or f of x axes. If my y-intercept is at -30, I'm just going to cheat. I'm just going to come down here and say that this is -30. I know that my slope is 5 and that my x-intercept is 6. So I'm just going to put a 6 here, and I'm just going to draw a line. This is, not even a good line. Okay, maybe I should have used the ruler tool. Please pretend that looks like a line. I know it doesn't. All right, number 22. Number 22 is an exponential function. And so far, all the exponential functions that we have studied do not cross the x-axis. So this one will not have an x-intercept. And like another way you could know that is you could plug in some different values for x. You're going to get numbers that get close to 0, but otherwise we could say the x-intercept does not exist. The y-intercept, however, is still the value of our function when x is equal to 0. So g of 0 is 5 times 2 to the power of 0 minus 1. Usually the x minus 1 is not in parentheses, but whatever. So that is like 5, times 2 to the power of -1, which is 5 times 1 over 2 to the power of +1, which is 5 halves. So our y-intercept here is 5 halves. And the growth factor is a +2. So again, I'm just going to cheat. I'm giving you permission to cheat too, by the way, like on this, not on a test, like on this homework assignment. Instead of actually graphing this, I'm just going to mark the y-intercept. I'm just going to say that this is the point, 5 halves. I'm not really using the grid, and I'm just going to sketch what this graph should look like. So I know that it's going to be increasing to the left and approaching 0, but we'll have that horizontal asymptote. Sorry, that is to the left, increasing to the right. I did not use the correct word just there. Man, these last two are so much easier than those ones we just did. All right, we'll knock these out real fast. For number 23, h of x, again, if I'm finding, let's do the y-intercept first, that's easier. The y-intercept is when x is 0, so I substitute 0 for x, so h of 0 is -2 times 0 plus 3, and that is just -2 times +3, which is -6. And my x-intercept is what I get if I set the equation equal to 0, because that is, again, on the x-axis where y equals 0, and h of x is equal to y. So 0 equals -2 times x plus 3. So you could either divide both sides by -2 here, or you could distribute that multiplication. If you distribute, you would then add 6 to both sides, and then divide both sides by -2. And we would get -3. So again, our y-intercept, I'm doing a really bad job of writing these as ordered pairs, and our x-intercept, where y is equal to 0. So x is -3, y is 0. Over here, x is 0, y is -6. All right, I'm not going to graph these. I know you can graph them. I'm just trying to finish this video. Oh, number 24. Why is this the easiest one? I think this is the easiest one because it's in y equals mx plus b form. I don't have x plus or minus a number. So my y-intercept is 0, -8 because that is my b value. My x-intercept I would still get by setting this equal to 0. I'm going to add 8 on both sides, divide both sides by 2. Oops, shouldn't put an equal sign there. I get 4 equals x. So 4, 0 is my x-intercept. Again, I'm not going to graph those two linear equations, but it would help to graph them.